Okay, this is everything you need to know to do the position versus time graph lab. Um, and so what we're going to be doing in this lab is just trying to understand the relationship between one-dimensional particle kinematics and the position versus time graph that represents that motion. And what we're going to want to be able to do by the end of this is see a motion and sort of estimate what the position versus time graph would look like, and going the other direction too, to look at a position versus time graph and to be able to read off of it what's happening with the motion. It's important to recognize that these are really position versus time graphs are really only used in one-dimensional motion. In two dimensions, you could do it with the components, but you'd have to have multiple graphs. So this is only one-dimensional motion that this is relevant to for the most part. And in order to make sense out of the position versus time graphs, there are two things that you have to be able to read off of a graph. So two important properties of graphs. Okay, this can be, what I'm telling you right now can be any graph. It doesn't have to be a position versus time graph. It doesn't even have to be physics. It could just be any mathematical graph. But these two important properties are, first, the slope of the tangent line. And just looking ahead, this is what I'll talk about in a second. This is going to be related to an object's velocity when it's on a position versus time graph. And the second thing is the concavity of the graph. And that's going to be related to the acceleration. Okay, so let me go through these in order. So the first thing that we have to talk about is the slope of the tangent line. Okay, so let's say that we have some graph. Well, I'll still write it as a position versus time graph, but this could be X and Y or whatever. This could be any mathematical graph. And let's say that this graph looks like this. And let's say that we want to know the slope of the tangent line here and here. Okay. Well, the way that you do that is you take two nearby points around that point and then draw the line that goes through those two. So that's the tangent line there. And for this one, I'll take these 2 points here. That's the tangent line for that one. And for interpreting these slopes, remember that if you have a line that's like that, that's a positive slope. If you have a horizontal line, that's a zero slope. And if you have a line like that, that's a negative slope. Well, if this is a position versus time graph, then a tangent line that looks like this one, the positive slope here, means that the velocity is positive. One that's horizontal, that means the velocity is zero and the thing isn't moving. And then a negative slope would indicate a negative velocity. Okay, so now let's talk about concavity. you know, how concave, in what way the graph is concave. That's what we're talking about here. Um, so any graph that isn't a straight line has to be part of either a shape like this or part of a shape like this, okay? If it's a straight line, no matter what the slope is of the straight line, it has zero concavity, no concavity. So these are the only two possibilities if it has concavity. This one is called concave up. And you can think of that as, the way I learned this in math a long time ago, concave up is like a cup, concave down is like a frown. If you have concave up, that means that the concavity is positive. And so if you have a graph that looks like this on a position versus time graph, that means the acceleration is positive. And if you have one that looks like any part of this concave down graph, that is a negative concavity. And in a position versus time graph, that would be a negative acceleration. It's easy to remember positive and negative if you think of these as mouths of people. So that guy's thinking positive, that guy's thinking negative. And like I mentioned a second ago, if there's no concavity and you just have a straight line and it can be in any direction, then you have no concavity and it's not positive or negative. And if you have a position versus time graph that's just a straight line, then there's no acceleration. That means that that thing has a constant velocity. Constant velocity and zero acceleration mean the same thing, since acceleration is measuring how quickly the velocity is changing. Okay, so now in a little more detail, let me talk about how this relates to position versus time graphs. So on a P versus T graph, the slope of the tangent line at a point is the instantaneous velocity. Okay, so for example, if this is a position versus time graph, and let's say it looks like this, okay? And let's say we want to know, is the velocity positive or negative here and here and here? Okay, let's check those 3 points. So this is going to be telling us if the velocity is positive, it means the object's moving in the positive direction. If the object's zero, it means the object is at rest. And if the velocity is negative, it means that at that instant, the object is moving in the negative direction. So first, I'll do it for the one on the left, draw the line through that, extend it out. So there's the tangent line. You can see that that has a negative slope. And so at this point that we want to evaluate it, the velocity is negative. So the object at that instant is moving in the negative direction. At the second point, draw the two nearby points, draw the line through it. And if I drew it right, that's a horizontal line. So the velocity is zero. So the object is at rest at that point. And then last, if we draw the two nearby points for the one on the right, the line looks something like that. You can see that that line has a positive slope. And so at this instant, the velocity is positive. Okay, so what we have overall, the story here is that this object starts with a positive position, and it starts out moving in the negative direction. And then it gets to a point where it's at rest. And then from there on, it's moving in a positive direction. Okay, so now let's think about the concavity. So the concavity is the acceleration. So that slope of the tangent line is the velocity, the instantaneous velocity. The concavity is the acceleration. And so, for example, if you have a position versus time graph that looks like this, that's concave up. And so this graph over the whole thing represents a positive acceleration. What about a graph like this? Okay, it's not that whole shape, that whole frown shape, but it's part of that shape. And so this represents a negative acceleration over the whole thing. We mostly have been dealing with constant acceleration, but there's no law that an object has to have constant acceleration. No object has constant acceleration forever. So what would it look like if the acceleration changed from positive to negative? You'd get a change in the concavity. And if I go back to the first picture I drew, where I was demonstrating the slope of a tangent, notice that here it's concave down for half or whatever. And so the acceleration would be negative for the first half, and then it's concave up after that, so the acceleration becomes positive after that. And right in between here, there's a point where the acceleration is 0 for just one instant where the concavity is switching, visually somewhere about here. It's concave down all the way until that black dot I just made, and then concave up after that. And again, what if the position versus time graph is a straight line? Well, that is no concavity, so no acceleration. Okay, so let's put this all together into an example that's sort of like the kind of problems you'll have to be doing in this lab. So let's say that a ball is thrown up into the air. From a height, not thrown up, you know what I mean. But this object starts at a height of 2 meters and it's thrown in the direction upward from a height of 2 meters. And let's say that we're going to choose time equals 0 at the instant the object is thrown, the ball is thrown. We'll choose our position equals 0 to be on the ground. And we'll choose the positive direction to be up. Okay. And this graph that we're going to draw and all this stuff we're going to do would be different if we made different choices about time equals 0, position equals 0, and positive direction. So keep that in mind. And in the lab, there are going to be a couple of things where you're going to have to choose to change the positive direction and stuff like that. Okay, so let's say that what we want to do with this is we want to first sketch the position versus time graph of this motion. Second, we want to identify where on this graph the object is speeding up. Third, we want to identify where the object is slowing down. And fourth, we want to identify where the object is at its highest point in its flight. This object's being thrown straight up into the air, so at some point it's going to reach its highest point and then start coming back down. Okay, so for part A, we have to sketch the position versus time graph. So what do we know at the start of the motion? That's usually a good place to start if usually you're given information about what happens at the start. Well, we're told that the object starts at a height of 2 meters. And our 0 is at the ground and our positive direction is up. So if you start at 0 and go 2 meters in the positive direction, you're at a height of 2 meters. Okay, so that's definitely the starting point. What else do we know when it starts? Well, we know that it's thrown upwards. So we know that it starts out moving in the positive direction. And that means that the velocity has to be positive. So I'm going to just make a little dotted line here. And that's going to be the slope of this position versus time graph at the start. Okay, so I'll start to draw it, but now we're going to have to think about what happens right after that first instant. Okay, what do we know about the acceleration of this object that's in free fall? We know that gravity accelerates it downwards, and down is negative. So we know that the concavity has to be negative. We know that it's going to be concave down. So it starts out with a slope like this, and then from that point it's concave down, and it's going to keep following a path like that until it gets to a height of 0, which is the ground in this case. So what we have here is we see that we have the first half of this graph where the object, any instantaneous slope you chose would be positive. Okay, so on that whole first half, this object is moving in the positive direction, still on its way up. And then once it turns around and starts coming back down on that second half, any point you look at, if you draw the tangent, it's going to have a negative slope. Okay, so the first half of this graph represents when the object's on the way up, and the second half of this graph represents when the object's on the way down. Okay, so now that's the position versus time graph. How can we identify where it's speeding up? Well, the thing to remember about where the object is speeding up is velocity and acceleration have to have the same sign. So let's think about the signs of the velocity and acceleration at different points on this graph. Well, we already figured out that on the first half of this graph, up to this point, here. Every point has a positive velocity. We know that, we can see that it's concave down everywhere, so we know it has a negative acceleration. And so in order for this to be speeding up, we need to find a place where the velocity is negative, so it's the same sign as that acceleration. And so this region here is, I'm going to just label that B, because that's where this object is speeding up. Once it gets to its highest point and starts to fall back down, that's when the object starts speeding up on the way down. Okay, now part C. What do we know about the requirements for the object to be slowing down? Well, we know that velocity and acceleration have to have opposite signs. Again, on this whole graph, we know that the acceleration is negative. It's concave down. So the region where the velocity is positive, that makes the signs of velocity and acceleration opposite, is that first half. So this is, that's the wrong number, wrong letter. This first half is what we want for part C of this problem. All the places where the velocity is positive and the acceleration is negative. To be slowing down, you could also have a positive acceleration and a negative velocity, but this acceleration is negative the whole time, so there's nothing like that. And then the last question, part D, is where is the object at the highest point? There's a couple of ways to think about that. The first is just look at the highest position you get, and it happens right here, right? There's no point that has a greater position than that. The other way to think of it is to think about the instantaneous velocity. So if we draw a tangent line at that point, you can see that the slope of that tangent line is 0. And we know that when an object reaches its highest point in 1D kinematics, that's when the velocity is equal to 0. And so that's another way to think about it. But this is the point for part D.